Assalamualaikum and good morning everyone. Today our group would like to present about mechanical testing and the result of mechanical testing. First of all, this is my members. I am Firdaus bin Makhyudin, Firdaus bin Nasripan and Halif bin Hassan. Let's go for introduction additive manufacturing. What is additive manufacturing? Additive manufacturing is the process of connecting material to produce item using computer-aided design CAD model data, often layer upon layer. 3D printing, additive fabrication, and free-form fabrication are other terms for additive manufacturing. Additive manufacturing is a unique way of directly producing things from a digital model utilizing a layer-by-layer material build-up process. This tool-less manufacturing technology may make completely dense metallic object with a great accuracy in a short amount of time. Metal additive manufacturing features such as flexibility of component design, part complexity, lightweight, part consolidation, and design for function are generating a lot of interest in aircraft, oil and gas, marine, and car application. Objective of this project is to compare the material properties of additive manufacturing and conventional manufacturing materials. Next, to compare the tensile test result and determine the strength of the materials. Lastly, to ensure the tensile test is run by using the same testing process. Benefit of additive manufacturing. First, faster turnaround on prototype and low volume parts. With a little setup and no tooling needed, additive printing produces prototype and short run products far quicker than traditional production. This can assist with both innovation and time to market. Second, less waste material. The additive method employs only the metal required to manufacture the part. However, some pieces do require supports that are later removed. This may be retrieved and account for a tiny fraction of overall material usage. Lastly, lower energy usage. Additive manufacturing uses significantly less energy than traditional production techniques and has the potential to reduce energy costs over time. Okay, AM application in automotive industry. First, rapid prototyping during R&D. Its capacity to swiftly manufacture functioning prototypes in only a few hours. This can assist product designer in testing and iterating more often and cost effectively, resulting in better end products. Second, weight reduction. Components that were previously built from solid, heavy metal material may now be produced using additive manufacturing. This makes it easier to manufacture hollow component and use other weight saving techniques while employing lighter material. Third, streamlining customization. Customization is a prevalent trend in the automotive industry. Additive manufacturing makes it simple and inexpensive to produce one-of-a-kind unique component. Manufacturing replacement part. Maintenance and repair facilities would be able to make nearly any replacement component with 3D printer on hand, eliminating the need to keep it in stock or order it to finish the task. Okay, this is the workflow. Designing a part to be 3D printed. First, the part need to be solid, that is, not just a surface. It needs to have a real volume. Creating very small or delicate features may not be printed properly. This depends greatly on the type of 3D printer that is going to be used. Third, part is overhanging, features will need support to be printed properly. This should be taken into account since the model needs to be cleaned by removing the supports. This may not be an issue unless the part is very delicate since it might break. Fourth, be sure to calibrate the 3D printer before using it. It is essential to ensure that the part sticks properly to the build plate. If it does not, at some point the part may come loose and ruin the entire print job. Lastly, some thought should be given to the orientation of the part, since some printers are more precise on the X and Y axis than the Z axis. There are three processes in this project. First, tensile test sample preparation dimension. Second, tensile test sample preparation CAD drawing. And lastly, impact test sample preparation CAD drawing. That's all from me. Thank you.
Methodology. For the tensile test sample and impact test sample preparation CAD drawing, using the dimension that is given, draw the project in 2D and 3D by using SolidWorks or other suitable software and save it for next task. The picture below is dimension for impact test specimen and tensile test specimen. Specimen preparation. Well and non-well specimen. To plate will be continued by welding process. The visual inspection will be determine the quality of the welding and record imperfection. The material will be cut by laser cutter based on what we have done in software like the picture below. 3D printer specimen and result after test. This is the specimen that have been used for the test. This is tensile test specimen. Mild steel, PLA Pro Green 20%, polycarbonate 100%, ABS Pro Red 100% and ASA Black 20%. And this is for impact test specimen. Equipment for tensile test and impact test. The first picture is for tensile test equipment and the second one is impact test equipment.
Okay, this presentation will be continued by me by Muhammad Firdaus bin Nasripan. This is the result and analysis. Okay, from this slide, this is the table 1, the tensile test specimen dimension for 20% of infill. As we see, there are slightly different dimension from before and after the test. We can see from the table from this slide. Okay, in this table, the table 2 tensile test specimen dimension for 50% infill. Also, we can see the difference from the dimension before and dimension after the test. And this is the table 3 for the tensile specimen dimension for 100% infill. As we see, also they are different. Okay. And this is the table 4 or the tensile test specimen dimension for the mild steel. Okay, we see this is the before dimension and after dimension. Okay, this is the analysis for the ABS ProRed 20, 50 and 100% infill and the mild steel. As we see, as we see, the highest for this test, the strongest is the mild steel, which is it break until the second of 4 seconds above, and the weakest of the specimen is the ABS ProRed 100%, which is it break at the 2 seconds. Okay, the figure 3.3 show the specimen of ASA black for the 20, 50, and 100% infill and the mild steel. Okay, as we see, this is the highest, also the mild steel, and the weakest from this is the ASA black 100%, and the second one is the ASA black 20%, and slightly strongest, or the under of the strongest is the ASA black 50%. It break and almost at 3.5 seconds. Okay, this is the PLA Pro Green for 20, 50, and 100% infill and mild steel. Okay, as we see the mild steel in this slide, okay, in this figure, it cannot be plot perfectly, because uh, the specimen data for the PLA Pro Green is highest, and the strongest is the PLA Pro Green 20%, which is it break until the 14,000. Okay, which is the highest and the strongest, which is the longest, and the well still is only slightly uh, take a time, and it cannot reach the level of the PLA Pro Green. Okay, for this is the polycarbonate for the 20, 50, and 100% infill and mild steel. As we see, the highest and also the mild steel, and the weakest is the polycarbonate 100%, which is the gray. Secondly is the polycarbonate 50%, and the second strongest is the polycarbonate 20%. It is the blue, dark blue. Okay, this is the table test specimen dimension for the impact test. Okay, this is the specimen and the width, and the thickness, and the cross-sectional area. Okay, as we see, this is 10.0 mm, 4.8 mm, okay, 549 meter for cross-section. Okay, ASM black 50%, 10.0 mm, 5.0 mm, 551 m. Okay, polycarbonate 10.1 mm, 4.8 mm, 555.5 meter, and polypro green 50%, okay, 9.9 mm, 4.8 mm, and 549.45 meter. Okay, this is the impact test graph and analysis. As we see, the ASA black. Okay, for the orange, for the blue, okay, for the blue, it is the highest, which is the 0.005 for impact strength. Okay, meanwhile the 100% is the second highest, which is it score of 0.003, and the weakest is the 0.002. Secondly is the PLA for the impact of strength. As we see, PLA, the highest is the 20%, 0.003, and the 50 and 100% share the same place, which is the 0.002. Also, the ABS, the highest is the 100%, which is 0.03, which is the 100%, and 20 and 50% share the same place with number of 0.002, and the PC, or the polycarbonate, is the highest is the 50%, which is the orange, 0.003, and the 20% and 100% share the same place, which is 0.002, and for the mild steel is score 0.2, which is highest, and the lowest from this is 0.002. This is the final energy. Okay, for the ASA, the highest is the orange, which is the 1.011. Secondly is the 20%, which is 0.83, and the second highest is the weakest is the 0.787, which is the SA 100%. For the PLA, the highest is the 20%, which is 0.43, 0.38 for the 100%, and the weakest is 0.35, which is 50%. For the ABS, 0.64 for 20%, 0.5 100% is the second highest, and the weakest is 0.49 for the ABS, which is the 50%. For the PC or the polycarbonate, the highest is 0.38, which is the 100% polycarbonate. Second is 0.379 for the 50%, and 0.35, which is the 20%. For the MySteel, its score the highest is 30.256, which is the highest, and the lowest, as we see, 0.35. Okay, this is the figure. 3.13 is about an observed energy. Okay, as we see, the SA, the highest is the 2.03, which is the 50%. 1.66 for the 20%, and the weakest is 1.58. Okay, the secondly, the PLA score highest is 0.86, second highest is 0.76, and the the weakest is 0.69, which is the PLA 50%, and the ABS, the highest is 1.27, second highest is 1.01, which is the 100%, and weakest is 0.96, which is the 50% for the ABS. And the polycarbonate, the highest share the same place, which is the 50 and 100%, which is 0.76, and the lowest is 0.69. And the MySteel score the highest, which is 60.6, and the lowest in this graph is 0.69. Okay, conclusion. In conclusion, additive manufacturing gives advantage to a technological advance in the industry. Besides that, many complex parts can be created by using additive manufacturing, and this will provide the opportunity to create various parts. Next, parts that have been created will be tested by using a tensor test machine, and the result will be recorded as reference. Other than that, we can see that different material can affect the strength of the part based on the tensor graph. Lastly, this project can achieve the objective and all the process while this project runs smoothly by the guided of lecturer and assistant engineer. Okay, that's all from my group. Thank you.